Welcome, Shaila ma'am.
Good evening, all. Welcome, ma'am.
Ma'am, can you hear me now?
Yes, ma'am. Yes.
Okay, thank you. Are you able to see my screen?
Yes, ma'am.
Okay, I'm just going to try slideshow. Hope you are able to see my screen as I share it with you when I navigate with the pages.
Yes. Yes, ma'am. We are able to see.
Okay, thank you, ma'am.
Welcome, ma'am.
Thank you, ma'am. Thank you so much. Hope everyone is all set.
Yes. Now let us wait for a few more minutes.
Sure, ma'am.
Dear participants, already our today's resource person is with us. So we'll start sharp by 6 p.m. Yes. Shall we start, ma'am?
Sure, ma'am.
Yes.
Yeah.
The essence of mathematics lies in its ability to make the invisible visible. Let us seek the divine blessings of the invisible Almighty. May His grace enlighten our minds with knowledge, guide our thoughts with wisdom, and strengthen our hearts with humility. Respected Chairman, Vice Chairman, Director, Principal, Head of the Department, esteemed resource persons, faculty colleagues, and dear participants, good evening all. It gives me immense pleasure to welcome you all to the fifth and final day of our International Faculty Development Program on innovative applications of mathematics in real world challenges. Every day of this FTP has unfolded new dimensions of mathematics. And today, we step into a very exciting theme, applications of engineering mathematics in everyday life. As Galileo once said, mathematics is the language in which God has written the universe. Indeed, engineering mathematics is that powerful language which connects theory to practice, equations to innovations, and classrooms to real life. Engineering mathematics is just confined to solve integral and differential equations. It lives in the bridges we cross, algorithms in our phones, the traffic flow on our roads, and even the rhythms we enjoy. Mathematics is everywhere, but if it is everywhere, why don't we notice it? Well, today's session promises to reveal the invisible mathematics quietly shaping our daily lives. Now, I invite Ms. Eldin Jiva, Assistant Professor, Department of Mathematics, to deliver the welcome address and to introduce our today's resource person who is going to enlighten us. Welcome, ma'am.
Thank you, Anita ma'am. Good evening to all. It's my honor to extend a warm welcome to all of you as we gather today for the fifth day of our faculty development program. Over the past few days, we have been privileged to hear from accomplished experts who have shared their valuable knowledge, shedding light on how mathematical concepts are applied to address complex real world issues across various domains. Let us continue our pursuit of knowledge and innovation, striving to harness the power of mathematics to address the challenges of today and tomorrow. Also, it's my privilege to introduce our esteemed speaker, Dr. Shaila Manavalan Varghese, eminent mathematics professor in the Department of Developmental Mathematics at Austin Community College, Texas, USA. Dr. Shaila Manavalan Varghese holds a doctoral degree in mathematics, specialized in computational fluid dynamics, and brings over 19 years of dedicated experience in teaching and research. She has published 22 research articles in reputed national and international journals and conferences and has actively presented her work at prestigious platforms such as the Indian Institute of Technology, Austin Community College, and Anna University. She participated in inquiry-based learning fellowship program organized by UT Austin and Austin Community College. Her academic journey reflects a strong commitment to fostering engaging and joyful learning environments for both undergraduate and graduate students. Dr. Shaila Manavalan Varghese has been recognized with the Best Paper Award at the National Conference on Recent Trends in Mathematical Computing, organized by VIT University, Chennai in 2013. Additionally, she successfully completed the NPTEL certification course on effective engineering teaching in practice with a remarkable score of 91%, ranking among the top 1%. She has qualified the Tamil Nadu National Eligibility Test for assistant professor and has been active participant in various seminars, workshops, and faculty development programs. Dr. Shaila Manavalan Varghese exemplifies excellent communication, leadership, and research skills, making her a profound research for knowledge sharing in today's session. Ma'am, We are honored you with us today and looking forward to your valuable insights. Welcome you, ma'am.
Thank you, ma'am.
Thank you, Ms. Eldin Jiva, for the sweet introduction to our resource person. Without further delay, I now invite our respected resource person, Dr. Shaila Manavalan Varghese, to lead us into today's session. Welcome, ma'am. The screen is yours.
Thank you, ma'am. Good evening, friends. I'm Dr. Shaila Manavalan Varghese. My task for this session is to share a few thoughts on applications of engineering mathematics in everyday life. Let me start with what is mathematics? Mathematics is the manifestation of human reasoning. It is a revelation of how human beings think. Human beings reason in two ways: inductive reasoning, deductive reasoning. Now, what is inductive reasoning? It is a process of arriving at a general conclusion by observing specific examples. Now, let's look at this pattern. Can you look at the individual cases here and fill in this blank? What do you think will be the next picture? That's right. It's going to be a circle with the dots going up to the next slot in the counterclockwise direction. What did we do here? We observe the specific cases one by one and we come up with a general conclusion. That's inductive reasoning all about. Although inductive reasoning is a powerful method of drawing conclusions, we can never be certain that these conclusions are true. For these reasons, the conclusions are called conjectures, hypotheses, or educated guesses. If there is one example for which your conclusion does not hold, then your conclusion is false. Such a case is called counter-example. Now let's discuss what is deductive reasoning. In deductive reasoning, you assume general statements to be true and you prove a specific conclusion. A conclusion that is proved to be true by deductive reasoning is called a theorem. Now let me point to you the beauty of how mathematics is used in everyday life. Yes, mathematics is being used as a tool or a technique or an argument in different fields. Hope you will start enjoying and loving math by the end of this presentation. Why engineering mathematics? Engineers identify the problems and requirements in their field. Mathematicians formulate them into a mathematical model and would give all possible solutions. Further, the engineers would analyze the solutions and would consider only those solutions that are meaningful to their field of study and develop their ideas based on these solutions. However, there has always been a lack of understanding between their ideas and expectations. To bridge this gap between the engineers and mathematicians, an engineer should know the background and usage of different mathematical techniques. This is Bloom's taxonomy, the most popular learning strategy. Remember, understand, and apply are the lower levels of Bloom's taxonomy. For example, Suppose that you are learning about polar coordinates r and theta. You know, polar coordinates give us a different way of locating points in plane. At the same time, remember, Cartesian coordinates x, y you have learnt already. Try to relate them. X measures horizontal distance, y measures vertical distance. Understand that for a person driving the car, Cartesian coordinates are helpful as it would help him to go left or right based on the x coordinate or move up or down based on the y coordinate. But for a pilot flying the airplane, we require the distance r as well as the direction theta. So for a pilot, polar coordinates are helpful. Understand the concepts and you should be able to apply them, which will help you to move forward with higher levels of taxonomy we have: analyze, evaluate, and creator. Now, as an educator, our goal is student success. The key for student success is student engagement. Student engagement is based on 3 factors: how well a student can interact with their professors in their learning process, how they can interact with their course materials, and how they can interact with their peers, collaborating with each other as a team in their learning process. To help our students in the learning process, remember, we usually review the concepts, ask questions, quiz, Kahoot games. It will motivate the students to learn and recall the concepts. Understand, apart from class lectures and notes, we can always provide them with useful resources, just like YouTube videos, graphing tools, or demonstration projects that help them in understanding the concepts by visualizing the concepts. Applying the concepts, we always give assignments and practice problems that help our students to apply the concepts they learn. The next is analyze and evaluate. These strategies work well when students do the discussion as a group and work with technologies like MATLAB or Mathematica and collaborate as a team under the guidance of their professors. Create. Finally, we motivate them to create a new whole solution to current problems in their field of research. Now let's look at some of the applications. Right from rockets to road construction work, robots to roller coasters, engineering mathematics has a wide range of applications. There are different types of systems based on our field of study. Our intention is to learn the components of this system. The physical phenomena under analysis is not always a constant. It is going to change with respect to different factors. To measure the changes, we make use of derivatives. Equations involving derivatives, we call them as differential equations. Now for a mechanical system, the differential equations governing the system are obtained by writing the force balance equation if it is a mechanical translational system, or a torque balance equations if it is mechanical rotational system at various nodes. We observe that the basic tools of calculus are used in this system mainly for the purpose of modeling the engineering problems mathematically and obtaining solutions. Similarly, the basic model of an electrical system can be obtained by using fundamental elements: resistor, capacitor, and inductor. Using these elements, the electrical network is drawn. Then the differential equations governing the electrical system can be formed by writing the Kirchhoff's current law equation by choosing various nodes in the network, or Kirchhoff's voltage law by choosing various closed paths in the network. Once again, we note that the basic tools of calculus are used here to model the problems of electrical system. Image processing. This is an area where matrices serve as a powerful tool. For the purpose of image processing, image is captured as a matrix of higher dimension. Features of submatrices are analyzed. These matrices are processed using either statistical analysis or using transforms. It is transformed into different components using frequency domain analysis. The noise component in the high frequency domain is removed by making the corresponding submatrix into a zero matrix or by setting threshold values. At this stage, inverse transform is applied to get back the required image. Once again, the new image is converted into matrix. Matrix of higher dimension is further divided into submatrices. These submatrices are again analyzed to make sure the image is processed to desired accuracy. Transform techniques. They serve as an important tool in the analysis of signals and linear time invariant systems. Transformations are used because it helps us to understand the problems easier in one domain than in another. The Z transforms. It is used to convert discrete time domain signal into a discrete frequency domain signal. It has wide range of applications in mathematics as well as digital signal processing. It is mainly used to analyze and process digital data. The Laplace transforms. They are popularly used for analysis of continuous time signals and system. The purpose of Laplace transform is to transform an ordinary differential equation into an algebraic equation, which makes it easier to solve ordinary differential equation. This allows us to even compose differential equations for control theory. The Laplace transform has a number of properties that makes it useful for analyzing linear dynamical system. The most significant advantage is that differentiation becomes multiplication and integration becomes division by S. Whereas the Fourier transform is an important image processing tool, which is used to decompose an image into its sine and cosine components. The output of the transformation represents the image in Fourier or frequency domain, while the input image is the spatial domain equivalent. Now, I would like to share with you a part of research work done by Dr. Sini, Dr. Ismail, and myself on mangrove species. Let me explain how mathematics, science, and technology are used here to analyze flow around mangrove species from a fluid dynamics point of view. The differential equations governing the flow are Navier-Stokes system of equations, namely the continuity equation and the momentum equations. Thousands of people who live along the coastal areas, mountain slides, and river banks every year become victims of natural disasters. The solution to this problem is mangrove forest. Mangrove forests protect the coastal area and act as obstruction against natural calamities like hurricanes, winds, tsunamis, cyclones, and floods. A mangrove is a shrub or tree that lives in salt or brackish water along the coast. The speciality of mangrove roots is that it has aerial roots which help the trees to firmly grow on the muddy coastline. In this research, the data on the mangrove trees in Pichavaram, Tamil Nadu, India is collected from MS Swaminathan Research Foundation Research Center, Chennai, Tamil Nadu, India. The Pichavaram mangroves, the second largest mangrove forest in the world. By using computational fluid dynamics to analyze wave interaction between roots and trees of two major species in Pichavaram, Rhizophora and Avicennia marina, is the work done in this research. Avicenna marina, commonly known as grey mangrove or white mangrove, and grow as a shrub or a tree to a height up to 7 meters in Pichavaram mangrove forest. It has aerial roots and a diameter that varies from 0.8 to 1.5 centimeter. Rhizophora is a genus of tropical mangrove trees, sometimes collectively called true mangroves. The diameters of the stilt roots ranging between 2 and 5 centimeter. Let's quickly look at the limitations of the literature survey. Now, regarding the experimental studies, it focused only on the general structure of mangrove forest instead of individual species. It involved high experimental cost and they were time consuming. And regarding the analytical study, even though the fundamental equations of motion are well understood, it was highly challenging to find exact or approximate answers in all situations. These studies used various techniques to linearize the nonlinear governing equations. Regarding the numerical studies, simulation operations were carried out using numerical models, and the research always concentrated more on the inside structure of mangrove forest than they did on the individual mangrove trees. Hence, this research work aims to simulate and analyze the flow patterns around mangrove roots and trees of different mangrove species. This research can influence our society and provide awareness of the importance of mangroves in coastal protection, development, conservation, preservation, and management of mangrove projects should be promoted worldwide. Now, I'm going to cover 3 topics in this presentation. Water flow around 2-dimensional Avicenna mangrove roots, extreme tropical wind flow around 2-dimensional Rhizophora mangrove roots, and a comparative study of flow patterns around Rhizophora and Avicenna mangrove roots. The objectives of this study is to simulate and analyze the steady and unsteady incompressible flow of water and wind during severe tropical storm, intense tropical cyclone, and very intense tropical cyclone around the roots of Rhizophora species. Also to investigate the efficiency of different mangrove species and compare and analyze the flow patterns around 2 particular species, Avicenna and Rhizophora mangrove roots. The research methodology. The mathematical model used is Navier-Stokes system of equations. The boundary conditions discusses steady, unsteady, and incompressible fluid flows with turbulent conditions. To simulate the flow, velocity is given as the inlet condition. Since velocity is closely related to pressure and density, as seen in Navier-Stokes system of equations, end results in terms of velocity can be easily converted to pressure and density. Hence, this method is advantageous over other methods. Solid particles are ignored, all body forces are neglected. Physical properties, namely the density and coefficient of water and air, are considered for simulation and analysis of fluid interaction with mangrove roots and trees. We use the finite volume method to do the numerical study. The first and foremost step in the finite volume method is to divide the entire domain under consideration into discrete cells or control volumes. Nodes are placed at the cell center. The grid is generated. Integration of the nonlinear governing partial differential equations over each control volume is the key process of finite volume method. This yields a system of discretized equations at the nodal points. The system is then solved to obtain the unknown values of velocity and pressure at the nodal points, followed by post-processing of the results. Grid validation is done using structured mesh. Grid alignment with respect to flow direction for the first order accuracy is maintained. Perfect mesh combination is done to identify the flow pattern by changing the number of nodes and shape of the mesh. Convergence of the solution is also monitored. A grid independent study is carried out to determine the necessary number of grid cells in order to obtain the problem's grid independent solution and a suitable solution. The solutions obtained at each node is further processed to get the flow variable values at any location. It is achieved by the standard interpolation techniques. Contours vector plots are the most commonly employed features here. Initially, simulation of water flow around two-dimensional Avicennia mangrove roots was performed to study situations during the flood. Both steady and unsteady turbulence flow was studied using three turbulence models, namely Spalart-Almara, K omega and K epsilon turbulence models. The CFD model of aerial roots of Avicennia mangrove tree is developed using ANSYS Workbench Designer model. In this study, a total of 223 roots with dimensions ranging from 0.8 to 1.1 centimeter were taken into account. A constant inlet velocity was applied in case 1 for the steady flow. The inlet velocity was also simulated as a step function because the flow of the fluid will vary with respect to time in reality. The inlet velocity was considered as 3 meter per second, 6 meter per second, and 10 meter per second for various time intervals. This picture represents the velocity profile at different positions. Different contours here represent different velocity magnitudes. Blue contour represent very low velocity and the red contour here represents very high velocity. The velocity profile resulted in different models is depicted here, and we found out that low velocity has been observed near the root area and the area that had more roots. So the blue color represents the velocity is made to 0. This is the pressure distribution obtained at various locations of the root. Convergence of the solution was also monitored in 3 different models. And this is the graph of unsteady turbulent model velocity dissipation by nematophores at different locations. So you see that around the root, the position around the roots, the velocity drops. From all simulation results, it was observed that the speed of the water stream steadily decreases to more than 50% of the initial velocity as the water flows into the nematophores mangrove root zones. In the next study, simulation of extreme wind flow around two-dimensional Rhizophora mangrove roots was performed. In this study, a medium dense tree of height considered as 5 meter and the dimensions of the mangrove roots, stilt roots are taken as the range between 2 centimeter to 3 centimeter. The model of this tree is generated using ANSYS Workbench 18.1 version. 3 cases were simulated. For simulating severe tropical storm, steady and unsteady wind flow with constant velocity of 100 km per hour was simulated. And for intense tropical storm, case 2, steady and unsteady wind flow with constant velocity of 200 km per hour was simulated. And to simulate intense tropical cyclone, case 3, steady and unsteady wind flow with constant velocity of 300 km per hour was simulated. The Mach number of all 3 cases were found to be less than 0.3, so the flow was considered as an incompressible viscous flow. The density and coefficient of viscosity of air was used during the simulation. The pressure-based solver is used to solve this problem. So this is the mesh created in ANSYS, and also a grid convergence study was done to analyze the mesh size and the number of nodes to be generated. The mathematical model used was Navier-Stokes system of equations. And these are the results that we got for the velocity of the wind flow at different locations of the routes. So we see that along the upstream side, for a steady flow, the wind flow is reduced to 36 meter per second, and along the downstream, it has reduced to 0. And in the perpendicular direction, it is 136.1 meter per second. These are the results that were obtained for steady and unsteady pressure distribution of the wind flow in case 3. So again, we see the steady and unsteady pressure variation of wind flow at inlet, outlet, and different positions. So we observed that the velocity was reduced to more than 80% of the initial velocity because of these root structures. In the next study, a comparative study of flow patterns was done around Rhizophora and Avicennia mangrove roots. Incompressible, unsteady viscous airflow was simulated around these two species, Rhizophora and Avicennia roots, with inlet velocity modeled as a step function. In this study, the flow is simulated using terminal turbulence model because of the Reynolds number found to be greater than 10,000, and the flow is considered as incompressible due to the Mach number, which is less than 0.3. This is the CFD model created in ANSYS. The total number of roots considered for Rhizophora and Avicennia are 112 and 224 respectively. It was taken in the ratio 1:2. Incompressible, unsteady viscous airflow was simulated around the Rhizophora and Avicennia roots using the inlet velocity of 10, 20, and 30 meter per second for different time intervals. We use the K epsilon model which incorporates the equation of continuity, momentum equations, as well as the transport equations to measure the turbulent kinetic energy K, and another transport equation to measure turbulent kinetic energy dissipation rate. So we compared the results of the velocity magnitude for Rhizophora and Avicennia. So we see that along the upstream for Rhizophora, it's 5.2 meter per second. And along the downstream, the velocity magnitude has completely reduced to 0 meter per second during its interaction of the wind with the wind and water with the roots. And in the perpendicular direction, we see that the wind is 11.3 meter per second. Whereas in Abyssinia, along the upstream, the velocity has reduced to 4.8 meter per second, and along the downstream, 0 meter per second, and along the perpendicular direction, 10.5 meter per second. So the velocity profile was measured during the time intervals of 4 seconds, 8 seconds, and 12 seconds in this study. In this study, Rhizophora and Abyssinia roots were considered in the ratio 1:2, which clearly reveals that Rhizophora mangrove roots can reduce the flow velocity to a greater extent because of its complexity and its root dimension in comparison to Abyssinia roots. Both roots had the capacity to reduce the flow velocity to a great extent. The comparison of the inlet and outlet velocity of both the mangrove roots shows that Rhizophora and Abyssinia mangrove roots reduce around 60% of the inlet velocity. The characteristics and coordination of mangrove roots, however, have a significant impact in reducing the flow velocity. The mangrove roots and trees play an essential role in reducing the wave velocity and protect the coast as a natural breakwater model. Under steady and unsteady state scenarios, it is noted that there is a little change in the simulation results produced by the three different turbulence models. Near the root region and the area where higher root density is observed, very low velocity has been seen. This study hopefully can influence the people to design breakwater models, plant more mangrove trees, and restore the existing ones near the coastal area to protect the villagers staying near the coastal area from natural disasters. This study encourages planting new mangrove trees and protect old ones because they are extremely valuable. This research also demonstrates that CFD is the most cost-effective technique for investigating problems in the real world. This study is therefore an evidence to show that computational fluid dynamics is the best tool to investigate problems in actual environment with minimum cost. So these are the limitations and future scope. Multi-phase fluid around different species of mangrove trees can be done. Flow around multiple trees. Flow around different arrangement of mangrove trees can be investigated. So we started this study with 2-dimensional and then later developed into a 3-dimensional study. These are some of the publications that were done based on this research work. So we see that the blend of engineering mathematics with science and technology in your area of interest will help you to solve the problems in the field of engineering successfully. Any questions?
Participants, any questions? I think someone is asking PPT, ma'am. Shaila, ma'am, we couldn't hear your voice.
Ma'am, can you hear me now?
Yes, ma'am. Yes.
Okay, I think it was like muted somehow. Sorry about it. So since this involves research work of other professors also in the team, I just want to discuss with them before sharing the PPT. If they give me a consent, then I can share the PPT.
Sure, ma'am. Thank you. Any other questions? Ma'am, there is one more question from Prabha. Do you involve the boundary layer problems here?
In this case, yes, ma'am.
Okay.
Few studies have involved boundary layers also. Yes.
Yeah, some comments are there. Excellent. So no questions, it seems.
Okay, ma'am. Thank you so much for this opportunity. I express my sincere and heartfelt thanks to God Almighty first for granting me the wisdom, health, and strength to undertake this task. I also like to extend my thanks to Houston City College, New Prince Sri Bhavani College of Engineering and Technology. Thank you, Dr. Anita Florence, for inviting me to this faculty development program. I also thank all the organizers and conveners of this FDP program. And last but not the least, thank you all participants for joining the session.
Thank you, Dr. Shaila Manavalan Varghese, for that insightful and thought-provoking session. Really, your presentation was started with inductive reasoning and deductive reasoning. And nowadays, I think almost all of the engineering colleges seeking for the approval of NBA. In that NBA, everyone should know the Bloom's taxonomy level. So the way you binded your engineering mathematics with Bloom's taxonomy is highly appreciable, ma'am. And the present world is surrounded with lots of natural calamities. So the mathematical model you have created with the mangrove species protect the coastal areas. So this work is
Anita ma'am, you are not audible. Anita ma'am.
I'm sorry. Suddenly it was unmuted. Thank you, Dr. Shaila ma'am,
Thank you, ma'am.
For the insightful and the thought-provoking session. See, nowadays all the engineering colleges are seeking for the approval of NBA. In that, Bloom's taxonomy is very, very important. So the way you binded the Bloom's taxonomy with engineering mathematics is highly appreciable. And also the world is surrounded with a lot of natural calamities. And somehow you are given the solution. So the model you have created with mangrove species. So it helps us to protect the coastal areas. Thank you so much, ma'am. So truly it has helped us to see how engineering mathematics is not abstract, but deeply woven into the very fabric of our daily lives. Thank you so much, ma'am.
You're welcome, ma'am.
Yes, ma'am.
If you don't have any questions, can I leave so that you can
yes,
continue
participants, since there is a time variation for us and ma'am, she has to leave for the work. So she's leaving the meeting now, but it is not yet over. Next, we have the vote of thanks session, then the feedback session. Thank you so much, Shaila ma'am. Thank you.
You're welcome, ma'am. Appreciate.
Yes.
Thank you. Appreciate your faculty development programs that you do to encourage faculty to gain more knowledge and understanding with the practical applications of math in day-to-day life.
Thank you so much.
All the best, ma'am. See you all.
Thank you. Yes. As we conclude today's session, And indeed, this 5-day FDP, we are reminded that just a minute. As we conclude today's session, and indeed this 5-day FDP, we are reminded that mathematics is not merely a subject, but a tool of transformation. It equips us not only to solve problems, but to shape innovations that impact society. Mathematics connects logic with the world. Gratitude connects hearts with one another. My heartfelt gratitude to our program coordinator, whose meticulous planning, tireless efforts, and constant guidance have been the backbone of this entire program. Now, I would like to call our program coordinator, Dr. Pushpalakshmi Gopalakrishnan, Assistant Professor, Department of Mathematics, New Prince Sri Bhavani College of Engineering and Technology, Chennai, to propose the vote of thanks.
Yes, ma'am. Good evening, all present here, respected resource persons, colleagues, and dear participants. As we reach the end of this wonderful, enriching 5-day journey of planning through the International Faculty Development Program on innovative applications of mathematics in real-world challenges, it is my honor to deliver the vote of thanks on behalf of the organizing committee. Gratitude is the fairest blossom which springs from the soul. With this spirit, I bow in gratitude to the God for his blessings that have guided us throughout this program. My sincere thanks to the eminent resource persons, Dr. P. Vijay Kumar, COE, Professor of Mathematics, Kiyat University, Gunupur, Odisha. Dr. Joseph Merlin, Senior Lecturer, Department of Mathematics, University of Eswatini, Uganda. Dr. P. Mallikarjuna Rao, Professor, Head of the Department of Mathematics, Raghu Engineering College, Visakhapatnam. Dr. Karupaya Kannappan, Assistant Professor, Department of Mathematics, Government College of Engineering, Kodinayakanur, Tamil Nadu. Dr. Shaila Manavalan Varghese, Math Professor, Department of Developmental Mathematics, Houston Community College, Texas, USA, who took time out of their busy schedules and enlightened us with their expertise. Their insightful sessions on the innovative role of mathematics in real-world problems have truly broadened our perspective and inspired us to integrate these applications into teaching and research. I express my heartfelt gratitude to our chairman, Mr. E. Loganathan, the man of vision. Vice Chairman, Mr. L. Naveen Prasad, man of mission. Director, Professor Swaminathan, pillar of New Prince. Principal, Dr. T. Saravanan, dynamic leader. Head of the department, Dr. S. Sivakami, friendly mentor, for their constant encouragement, guidance, and support in organizing this FDP. I sincerely thank our faculty colleagues and organizing committee members, Dr. F. Anita Florence Minola, co-coordinator. Mrs. C.R. Eldinjiva, Mrs. G. Geeta Ramani, Mrs. P. Nandini, Dr. R. Subhadra, Dr. Karthikeyan, Dr. Sundarapandian, and Mr. Arpuda Jones, who worked with dedication, ensuring every aspect of this program runs smoothly. I am grateful to Mrs. P. Usha Nandini, Assistant Professor, Department of English, Dr. Hema Malini, Assistant Professor, Department of Tamil, without whom the smooth execution of this event would not have been possible. I also extend my warm gratitude to all the faculties of Science and Humanities, New Prince Sri Bhavani College of Engineering and Technology, Chennai, for their constant support through motivation and guidance. A special appreciation goes to all our dear participants. Your enthusiastic involvement, keen interest, active engagement through thoughtful questions and constructive interactions added immense value to this FDP. Without your involvement, this program would not have been more meaningful and impactful. As we conclude, let us carry forward the insights we gained and continue to bridge mathematics with real-world challenges. Let us start today with a renewed spirit to apply mathematics innovatively and make a difference in our teaching, research, and society at large. Mathematics teaches us that every problem has a solution. Gratitude teaches us that every solution is a gift. Thank you, one and all. Thank you.
Thank you, ma'am. Dear participants, so now all of you unmute yourself and on your videos for photo session. And there is a common feedback session is there. If anybody is interested to share about your share your thoughts about FTP and the presentation, you can share it now. Because always your feedback will motivate us to conduct this kind of FTPs in future.
Now unmute only. Please
Dear
give
participants,
feedback.
you can unmute yourself on your videos. So I think,
Hi, Pro.
welcome, sir. Welcome, sir. Welcome.
Welcome, sir.
Thank you very much. I am sorry I was in class. I could not join timelessly. I could not join when you started.
No problem,
But
sir.
so I think it's to thank you for organizing this program. I'm from a very different part of the world. I don't think we knew each other. I truly appreciate the invitation. And I know that sometimes when you come and present your work, it can sound like rocket science to another person. But if someone has interest in mathematical modeling, specifically mathematical biology, they can always write to me an email if they want further discussions, or if someone has a burning question about my talk here, I'm happy to answer. Yeah, I think that's it. I'll rewrite my email address, but it was just to say thank you and to apologize that I couldn't make it to this session early enough. I was in class.
So no problem, sir. You're joined in the right time.
You are
Because just
muted.
now we have started.
Oh,
Yeah,
okay.
you are. Yes. Just
I've
now we
joined
have
at the
started
right
our
time.
feedback. Yes, yes, yes.
Okay, okay. So is there anything I am supposed to do in this particular session? Is there something that is required from me?
Yes. Participants, do you have any queries about his session? You feel free to ask from sir.
The messages I'm seeing are all thanking you.
Yes.
And I attended the talk by, I don't remember which professor, who was then talking about applications of differential equations.
Differentially, yesterday's
Yeah.
talk.
I thought it was an excellent talk. I think that's the only talk that I attended just a little bit. I thought it was excellent in a way that he covered from the very basics.
Sir, I think
So
he's in line, sir. I think he is also in meeting, sir.
Yes, so but I don't have any question. I'm just saying I liked the talk in the sense that he moved from the very basics, from scratch. And if by any chance I get a chance to be invited again, I think it would be nice for me to as well start with basic mathematical models, you know, not to just come and present, you know, because the paper that I presented is just the research that I'm currently working on with other colleagues from around the world, other professors from around the world. So I think it's important to also, you know, deal with the very basics. So I'm just thanking that person. I could not attend the other sessions, but I want to believe maybe they also took a similar approach of covering a topic from the very basics. Thank you. I think those are my comments. It's just to thank you. I'm happy to answer any questions if there are any.
Pushpa ma'am, please enable the participants to unmute themselves, ma'am.
Yes, ma'am. Already unmuted only.
Okay.
Yes,
Dear-
unmuted.
Because Longway, your resource person has joined today also to clear all your queries. Joseph sir. Joseph sir, are you in meeting?
Yes, ma'am. He is there only. He is here only.
Yeah.
Sir, kindly unmute, sir.
Yes, I'm here.
Thank you very much. On that day, you have explained about, yes, you have explained about the two oncolytic viruses, VV and VSV. Your voice, your presentation, really, we admire, sir, the presentation. It was so good. Thank you so much. Unfortunately, we couldn't record the
Thank
video
you.
clippings on that day.
Yes, I felt bad, but it's okay. There is always another time. I
sir.
needed the recording for myself. So for future reference for myself to see how I delivered the talk, but it's okay.
Yes.
Mm.
The participants, if anyone wants to share something, you can share.
Maybe I should mute myself.
I think
so that some
Dr. Dorothy raised her
yes.
hands. Yeah.
I do have my hand raised. Good morning, where I am. I'm in Houston, Texas. I came on to support my colleague, Dr. Shaila Varghese, and I came a little bit past the time, so I was unable to hear her participate in this event. But I wanted to know how can I get more information about the event? Is it open to other professors, and do you discuss topics that are not necessarily totally mathematics? Like, do you do pedagogy as it relates to the teaching of mathematics? Just what's the scope of this presentation?
Okay. So, in future, if we conduct any conferences, ma'am, in that we will discuss about this elaborately.
Okay. All right.
Yeah. Yeah, we are very happy, ma'am, that you joined with us.
Thank you.
Yes. Anyone else wants to share? Okay. Your word of motivation will help us to conduct. Yes. Ma'am, have you taken the snap, ma'am? Pushpa, ma'am?
Ma'am, yes, ma'am, I did, ma'am.
Yes, yes. Yes. Or else, shall we wind up the session? Yes. Thank you all once again. Have a dream with mathematics. Good night. Joseph sir, if you want to share something, you can share.
No, ma'am.
Okay.
I think I said everything I wanted to say. It's to say thank
Okay, sir.
you. It's
Thank
to
you so much.
say maybe in relation to what the previous speaker said, I'm not the organizer. I would be wisecking to say this, but maybe the suggestion still would be to take the to give the talk in a way that the second presenter did. Is it second, the third, the one who was talking about applications of differential equations, to move from the very basics, such that if there are early career researchers or PhD students or master's students, they also benefit. Or if there are people who are not in that field of research, they get to benefit in the sense that they would get to know the basics before higher order stuff is presented. I mean, I'm saying this, I'm not the organizer, I was only invited. I don't know anything, I don't know the scope, I don't know the objectives of the whole program. So, but that's just a comment anyway. That for whichever scope or topics that are being considered, the presenter aims to, start from the very basics, from the simplest stuff. And yeah, so that's it, Prof. There is really nothing much from my side.
Thank you, sir. Surely we'll take up your words, and in future we'll arrange those type of sessions.
All right.
Yes. Thank you, sir. Thank you so much. Shall we wind up? Yes, anyone else wants to share? Or else we'll wind up.
Thank you, ma'am. Thank you, Anita, ma'am.
Okay. Okay. So thank you so much. Thank you so much, sir. I thank everyone who have joined. Thank you so much. Good night.